Okay. So, hello again, everyone. So it's my pleasure to be chairing this second session of the day, so the first one of the afternoon. And so we will start with a talk by Kwang Yong Choi from Singh University, who will talk about spin-ons and magnetization plateaus in Kagome antiferromagnet. Thank you very much.
Okay. Thanks, organizer, for inviting me to this wonderful workshop. Originally, I'm supposed to give a talk in person, but I had some visa issues. I regret I missed the chance to have a face-to-face meeting and hang out with some friends and renowned scholars on occasion of this nice workshop. Anyway, I hope to visit India in the near future. Today, as announced, today's my talk goes on the spin-ons and magnetization plateaus in the recently discovered yttrium copper-3 bromide Kagome antiferromagnet. I think in this workshop, you already heard the similar talks, very exciting talks on the related topic, but flavor of my talk is a little bit different. I try to mainly emphasize, highlight the rich physics of field-induced, magnetic, exotic magnetic state emergent in Kagome antiferromagnet. Okay, good. I think it's you guys, most of you are familiar with the quantum spin record. Nonetheless, for the educational purpose, let me repeat some basic stuff. In a nutshell, quantum spin record highly correlated and entangled state of matter that features the fractionalized excitation, such as spinons and anyons and magnetic monopoles. These emergent fractionalized excitation are coupled to emergent gauge field. In spin record, gauge theory actually gives us very simple way to categorize the flavor and type of quantum spin record. G2 spin record or U1 direct or K-type spin record and so on. Also, let me spend a little bit time in, illustrating this important key concept in spinized material. Everybody know what is the spinized material, and the ground state of spinize has a two-in and two-out spin configuration as sketched here. Okay, then if you imagine the spin as a magnetic flux line, then here you see fictitious magnetic field become a divergence free and satisfy this static Coulomb's law. And this means that magnetic field divergence free means that magnetic field forms long closed loop. And then just consider two spins located in the here and there, and they are far away. And you see they are coupled to each other. In this way, you can understand how the long-range correlated state emerges due to Coulomb gauge. Again, we can explain how the emergent, here is the spinized, the magnetic monopole emerges from this simple cartoon. Okay, the low energy excitation in spinize can be created by flipping one spin. Here is the black arrow and tetrahedron. Then this green tetrahedron has a 3 spin in, 1 spin out configuration, and his blue tetrahedron and 3 spin out and 1 spin in configuration. And this, the center of this green tetrahedron is now become the sink of magnetic field, and then green tetrahedron become a source of magnetic field. In this way, we can create the magnetic negative and positive magnetic monopoles. Actually, this magnetic monopole is some non-local entity in the sense that you can create magnetic spin flip without costing any energy, and this negative and positive magnetic poles can be separated out in the infinitely. Okay, and I think the promising place to look for quantum spin record is two-dimensional spin half system. This is because according to the Hastings theorem, if no symmetry is broken, 2D quantum magnet should have a non-trivial paramagnetic state. More specifically, in the absence of time reversal symmetry or translational symmetry breaking, the chance is really high of achieving kind of some quantum spin liquid, non-trivial quantum paramagnetic state, like the RBB liquid. Here is visualized. Here is the blue oval symbol represent the spin singlet, and RBB state is the superposition of all possible dimer configuration. The next question is how to evade the symmetry breaking. The well-known parameterizing way is to introduce the geometrical prostration, best realized in here the triangle motif. Okay, then previous speaker already discussed in the pyrochlorotype tetrahedron local constraint. Here is the triangle cluster. We have again local constraint, the geometric constraint. That means that some of these 3 spin should be identically 0. And if you consider each cluster has fulfilled local such a constraint, then we will gonna have some macroscopic degeneracy of ground state. And again, this gives the 0-point entropy and eventually the breakdown of quasi-particles. As you may know, this concept, geometrical prostration in 2D case is maximized in the corner sharing of triangle, known as Kagome material. After more than 20 years of tremendous research effort, we are slowly reaching a consensus on the ground state of spin-F Kagome antiferromagnet. Although there is still some debate on the exact precise flavor type of spin liquid, most likely the spin-F Kagome antiferromagnetic hosts a kind of spin liquid. The question is which type of spin liquid, as listed here in this table. Okay. 2 type of spin liquid ground state is the oscillate. Depending on the employed numerical technique or mean field and ansatz, some calculation ended up with gapless U1 and the other is gapped G2 spin liquid. Also, one of the organizer, Yasir, contributed to this physics, and it turns out that ground state energy difference between these 2 states is vanishingly small. That's the reason in real material, I think it's hopeless to discriminate between these 2 theoretical scenarios. Even worse, you may learn from the previous or series of previous speakers. Now in the quantum spin liquid material, quantity order matters. As real material contains a lot of defect and perturbation and quantity disorder. Actually, this quantity disorder induce random or inhomogeneous singlet state. Then the question is how we can discriminate actually the disorder-induced singlet state and the authentic gapped spin liquid. That will be the really issue nowadays in the material-wise. Okay, and in addition to possible zero-field spin liquid, Kagome lattice accommodate the rich field-induced phase, usually which is manifest in the magnetization process. Okay, in the semi-classical case, you see the magnetization plateau. Actually, this is a solid phase. Field-induced solid phase appears when the so-called commensurability conditions are satisfied. Written down here, number of magnons in the magnetic unit cell should be integer. Here is a Q mark, means the number of spin in the magnetic unit cell. S is the spin number, and small m is the magnetization relative to its saturated value. Okay, in the Kagome lattice, you see Kagome lattice, the spin lattice, spin liquid is quite fragile and unstable toward in the Q0 or square root 3 times square root 3 magnetic ordering under some perturbation. And that's the reason we assume that the magnetic unit cell in the Kagome lattice looks like this square root 2 times square root 3 superstructure called or hexagram. In this case, you can count 1, 2, 3, 4, 5, 6 spins on the hexagonal plaquette, and the edge spin again 6, but this edge spin shares by the nearby adjacent superstructure. That means that halved, then 6 plus 3. That means that we have some 9 spins in this magnetic superstructure. Then at the end of day, we will gonna have some 3 magnetic plateau, just applying this commensurability condition to our Kagome case. Then 1/3, 5/9, and 7/9, 3 plateaus. Okay. In this panel, I summarized calculate the magnetization curve, magnetization versus external magnetic field. Theory like that. This is the magnetic field scaled by exchange coupling constant 3J here. And you see here with the increasing the magnetic field, you see first the 1/9 plateau and 1/3, 5/9, and 7/9. Actually, these 3 guys actually what is predicted from the commensurability condition. That means that the origin of this magnetic plateau is semi-classical and can be understood in terms of Magnon crystal, in terms of this kind of hexagram superlattice. And in the hexagram superlattice, this kind of hexagram superlattice is decomposed into some edge triangle spins. And then here is the spin on the hexagonal plaquette. Actually, this is a 6 spin on the hexagonal plaquette forms kind of some finite Magnon state. And this Magnon state is quite localized because the hopping along this path and this path in the perfect Kagome case destructively interfere. This is the typical signature of the Kagome physics, metallic or insulate. It doesn't matter. And this is origin of flat band. But anyway, on the other end, we can see this is the DMRG calculation ledger. This is the some tensor network calculation ledger done by Dieter. He's one of the previous speaker in this workshop, although his topic was different from this one. And okay, this is the 1/9 plateau is the, nothing to do with the classical origin. Then Magnon crystal, that means that this is of a purely quantum mechanical origin. Okay, here is I a little bit introduced the Magnon density pattern calculated by DMRG calculation. Okay, for 1/3, 5/9, and 7/9 case. Okay, this black bar represent a degree of spin polarization. Okay, the longitudinal magnetization induced by external field on this at each side. You see in the here is the edge spin is fully polarized, and then here is the 1/3 plateau, 5/9, 7/9 corresponding to 0, 1, 2 Magnon state on the hexagonal plaquette. This is quite a naive and simple scenario. This is superstructure, and okay, the Magnon crystal kind of pattern can give us some very first idea. How looks like the some solid field in the solid state of classical, semi-classical origin, but subsequent study of the tensor network calculation revealed that the real story might be more complicated. For example, in the 1/3 plateau, not only we have this kind of superstructure field in this Magnon field superstructure, but also we gonna have some mimetic phase, and this is the bonding means that kind of average maybe spin-spin correlation. Also, we should think about it in that kind of this magnetic field induced magnetic moment located in between these bonds. But anyway, I wanna go into detail because this is too far away from my present data, and then I refer to original Dieter's calculation if you're interested. Okay, this is again the Dieter's calculation. This is the spin number dependence of magnetization plateau. You see, this is the 3 of semi-classical origin ubiquitous to the or spin numbers, but 1/9 magnetization plateau, quantum plateau is unique to spin half Kagome system. That means that 1/9 plateau is can be considered as a hallmark of 1/9 Kagome spin half Kagome antiferromagnet. but it's theoretically this is very complicated. It's some structure has been proposed. Here you see this kind of some dimerized state, and here is the superstructure. But sure, this is we have no relevant material to test this theory, and that's the reason this in this my talk I claim that we have some candidate material. I just introduced, we found that candidate material. Okay, with this theoretical background in mind, let's move to the real material. Okay, the key player of this work was my master student, Seungmin Jung, and then I have collaborated with other friends for Raman and high field magnetization specific in thermal conductivity measurement. Okay, on the material side, the atacamite offers the rich reservoir of a spinel copper-based Kagome antiferromagnetic. Okay, in this chemical formula, you see M represent the divalent 3D metal ions or trivalent layers ions. Then X is the halide or nitrate or sulfate. Okay, as summarized in this table taken from this paper, you see up to now, 30 to 40 derivative has been reported in the literature, has been investigated, but the single crystal is known only, I think it's less than 10. And although this looks complicated, all these variants can be grouped into two main structures, the Herbertsmithite and Capella-site. The Herbertsmithite structure contains ABC stacked Kagome layer separated by non-magnetic triangle planes. And if you substitute some kind of these metallic ions, then usually the metallic ions go in between the Kagome layers. In the Capella-site in the structure, okay, then it's this Kagome layer stacked in our AA sequence, and then if you just substituent M usually go into the center of the Kagome layer. This is the two main variants. And okay, then maybe in the I think it's that I'll not give a very detailed discussion of this one. Maybe in the, I don't know, next day, and another speaker will give a detailed presentation on the Herbertsmithite. Just I wanna mention that, okay, this is over the 10 years, this is the most extensively studied some material as a promising candidate. But at the end of the day, people realize that this kind of Zinc 2 plus copper 2 plus anthracite mixing blocked and masked and intrinsic Kagome physics. Almost 15% of copper 2 magnetic ions occupy the non-magnetic zinc site. Okay, this is weakly or open spin-like stuff. Anyway, give rise to very strong Curie tail in the magnetic susceptibility. Then also the as Imai presented, also induced the inhomogeneous ground state consisting of some random singlet and the quantum disorder state. Also, unfortunately, this also anthracite missing totally suppressed the 1/9 plateau. This dashed line theoretical prediction for 1/9 plateau, this is the red and blue line, this is the experimental data. Okay. Okay, this is our compound. Unlike the Herbertsmithite, is okay, yttrium copper 3 nearly free from that kind of some interside missing of magnetic ion. But unfortunately, here we have some brome and hydroxyl, this kind of substitution, and the random distribution between these two guys in this position. Here is okay, hydroxyl and brome, and these guys turns out to locally distort structure, and then consequently particularly 70% of these yttrium ions moves from its original ideal place. And if you consider we have three cases. Here is we have some brom and hydroxyl ion, or brom and hydroxyl. In these three cases, it turns out that this kind of local structural distortion modulate the kappa oxygen kappa angle. Here's 115.5 and then here 112.7. We have three different kappa oxygen kappa super exchange angle passed. That means that we're gonna have three different exchange interaction in a very simple model. Okay, then we can, but good thing is that in spite of this kind of local distortion, the Kagome kappa 2 plus ion site is hardly affected. Yeah, this is a good thing. But anyway, then the minimal model of this is yttrium kappa 3 can be captured like that way. Then the Kagome antiferromagnetic system with the three band randomness. Okay, J1 and J1 plus delta J minus delta J in the. Okay, the average exchange interaction is order of 60 Kelvin. This is way smaller than 180 Kelvin of Herbertsmithite, just because the bonding angle is smaller and the distance is different. It turns out this band randomness model captures nicely the temperature dependent of magnetic susceptibility. This is the kind of orangey square is experimental data, and then this purple line is a theoretical simulation result. Okay, this model actually with this kind of number, J 60 Kelvin around, then captured all this harmful and low temperature upturn. Okay, then the here I plot the thermal conductivity divided by temperature versus temperature measured by Christian Hess group. And as you see from the by extrapolating this kappa to 0 Kelvin, you see the residually linear term is become vanishing small. Here is red symbol, here is almost 0. That means that this compound does not include the itinerant gap excitation. And okay, this group went into one step further, tried to isolate from the spin phonon scattering contribution from purely phonon contribution, and they somehow succeeded deduced the spin gap. This is number 1.4 Kelvin. But I don't know, this does not necessarily means that the ground state, this gap is gapped the G2 spin located, because as I mentioned, we have some perturbation and exchange randomness. In that case, we cannot, at the moment, cannot exclude the inhomogeneous singlet scenario anyway. Okay, this is our sample grown by the hydrothermal method. Is the sample size more than 2 millimeter size. And okay, this is our result. Magnetic specific heat versus temperature on a semi-logarithmic scale. You see, here is the blue circle. It's experimental data. Here is the solid line. Here is the pink and green line, theoretical calculation. Yeah, in the literature, several group has independently calculated the magnetic specific heat. Okay, you see from this data, we find a good agreement between the experimental theory, at least down to 20 Kelvin, including the 0.67 J maximum peak. Okay, this kind of first-rate low-dimensional system, this broad hump is quite typical for thermodynamic signature. And if you look at more carefully below 20 Kelvin, you see the theory, the predicted 0.1 J harm is quite suppressed. Instead, we have some additional small sharp peak at 2 Kelvin. But I think that is already in the years ago, Joker's group has shown that this kind of DM interaction actually induced the magnetic ordering. Actually, this kind of peak is growing with increasing the DM interaction. That's the reason is this kind of some peak, 2 Kelvin peak, something to do with some kind of band randomness induced DM interaction. I think it's the amino might not be globally well defined and not that much big in our sample case. And here I turn to some thermal conductivity versus temperature. You see thermal conductivity growing up with a small kind of shear hump all the way up to more than 100 Kelvin. This is not typical for pure pononic behavior. Most pononic case thermal conductivity shows some maximum around 20 Kelvin and dropped. This is quite typical. That means that this already gives some first impression that the thermal conductivity contains some contribution from the kind of fractionalized excitation through spin, maybe phonon scattering mechanism. Okay, here again, I plot the copper over T versus T, then we can clearly see this double peak hump and the deep structure. And interestingly, I found that the energy scale of this higher hump corresponding to, here is the chi times day. Here is the chi is the, within the U1 direct spin Ricky scenario, this is chi is the something to do renormalization parameter of the Spinon bandwidth. That means that here is this energy scale, Spinon bandwidth renormalization constant times J, coupling constant around 62 Kelvin for our case. Okay, and also this deep structure is something to do with some modulated in the band randomness, chi J minus delta J, means that this is really something to do with some kind of spin-on excitation. For temperature below this chi T energy scale, maybe the coherent spin-on still contribute to the transport behavior. Let me add a few words in the low temperature side. In the below 2 Kelvin, you see in the magnetic specific heat versus temperature shows the quadratic behavior in a very limited window, temperature window. And then as shown here in the inset, also thermal conductivity quadratic dependence. But I think it's people usually say that this kind of quadratic dependence is what is signature of a U1 direct spin rickety. But although this is occurs very limited window, also this coefficient relatively small. That's the reason. Based on the data in my hand, I cannot conclude what is the true ground state, because in this sample, I think a lot of people now pay attention to this compound. That's the reason in a future couple of years, we have a more idea what is the true ground state. Okay, then let me turn to some Raman spectroscopic signature of some fractionalized excitation. And unfortunately, the calculation has been done only for U1 direct spin rickety case. The Raman vortex issue is very notorious. That's the reason, unlike U-tron, although this is very nice scattering, method, it's very hard to directly compare to theoretical calculation. But anyway, in the U1 direct spin-on case, yes, the magnetic Raman magnetic intensity profile consists of two parts. It's one spin-on and anti-spin-on excitation, pair excitation, and two spin-on and anti-spin-on pair excitation. In the Raman scattering cases, the total magnetic moment should be conserved. That's the reason we simultaneously create the spin-on and anti-spin-on. And one more thing is that these people look at very carefully in the low energy excitation. They found that the low energy Raman intensity profile obey the superlinear power dependence. That means that omega alpha dependence. According to the theory, this is very close to number 3. And this kind of superlinear power dependence is the hallmark of this kind of spin-on band. It's this kind of emulate very special kind of some spin-on band structure. Okay, then this theory has been tested by this Chinese group on this Iqbal. And I just emphasize that here is only T2G channel, and here is the magnetic Raman scattering. You see, as seen by the color shading, this is the one pair component, and this is two pair component of spinon excitation as predicted by the theory. Okay, our group has to repeat the same knowledge to this yttrium kappa 3. This is the summary of our result, and you see here is I removed all the phonon excitation. Then here we plot the 2D plot. This is color counterplot, and with increasing the temperature, this magnetic excitation undergoes a gradual thermal damping and eventually melt into quasi-elastic scattering. This is quite typical for kind of spin-rigid candidate material. Okay, then we made a Bose correction to obtain this kind of magnetic Raman susceptibility, and then in that way we nullify this kind of thermal effect. And here in this spectrum you see also our magnetic spectra is consists of two components. This is the one spinon and antispinon. This is the two spinon antispinon pair excitation. But we found a little bit residual one. Sure, that's our sample has some exchange randomness. Okay, here is the color plot. Color counter plot, you see we can define this characteristic energy scale. J is 62 Kelvin. But let me give one word between the polarization dependence. Mainly the calculation also done not only in the EG channel, but also in the parallel polarized and then A1G channel. And according to the calculation in the A1G channel, this is a two pair component gain a spectral rate against the one pair spinon antispinon excitation. Okay, we found the overall trend is nicely agree with the theoretical prediction, and this is very good. And here we look at more carefully in our low energy excitation. Here is the low energy side of our Raman susceptibility, and it turns out that this low energy side can be described by the kind of power law dependence. And then as you see here, we have two power law regime, 1 to 5 MeV and 5 to 10 MeV follows the different power law behavior by fitting this data to this power law dependence. We can extract the exponent for 1 to 5 MeV regime. Alpha versus temperature, you see over whole temperature, alpha is smaller than 1. That means that in this excitation governed by the sublinear power dependence, but for from to 5 to 10 MeV energy window regime, this power, extracted power shows that with the decreasing temperature to switching from the sub to superlinear power dependence, and that's maybe reasonable. I cannot say that we based on only this data we have some evidence for kind of direct spinon signature, but this is I think it's very promising. Also, we have some perturbation. That's the reason low energy sides always deviate from, although this is the Kagome, I don't know, that's followed described by the Yuan drag spinon or not, but in the high energy side, relatively high energy side remained robust, but low energy side always will deviate. This is my final slide. And here is I summarize the magnetization measurement measured by the pulse field magnetization up to 6 Tesla. Here is the magnetization versus the external magnetic field. With increasing field, now is the magnetization increased and shows this kind of plateau. And again, increasing here tend to also reach to another magnetization plateau. This is the blue line theoretical calculation taken from the literature. Overall agreement is very nice. And then around the 21 Tesla, we can identify the 1/9 magnetic plateaus, expected by the perfect Kagome antiferromagnetic. And then for 1/3 plateau, I see still this is the actually magnetic plateau is a little bit smaller than the expected one. I'm not sure this is something to do with the band randomness. Band randomness perturbation maybe perturbed some superstructure at the 1/3 magnetization plateau, but definitely we should a little bit go higher field. Then I applied actually the ISSP more higher field 200 Tesla magnet time. Hopefully we can carry out the experiment in the coming October. And then we clarified actually this one. One more good thing is that this yttrium copper 3, the exchange coupling constant only order of 60 Kelvin. Then means that if you multiply 3 times 190 Kelvin, almost 200 Tesla, we can reach really full saturation. Then that means that this is the quite unique material which allows to maybe draw whole pictures in the magnetization plateaus in the Kagome system. Due to the exchange coupling constant is just 1/3 of a Herbertsmithite and the other well-known baroid and these things. This is the advantage of working on this one. Also, I have not discussed, this is the very first my idea, very first data. And that's the reason we have a lot of things to do. Even the around 1/3 plateau region and kind of superfluidity also has been predicted. And then I don't know, this possibly this is really will be a future issue. And then I want to compare our magnetization result with some sister compound counterpart, the yttrium copper 3 and chloride instead of bromide. But unfortunately, it turns out that this sample shows that magnetic ordering around 2.1 Kelvin. Then this will gonna be some magnetic order counterpart of our material. And then again, this is the first field magnetization data. At a first glance, these two guys looks quite similar. Okay, but if you see the number, then this is kind of in the field range in the 18 to 24 Tesla. You see the very well defined magnetization plateau, more stable, robust than the ours one, but actually the number is a little bit higher than 1/9 magnetization plateau. Maybe it's, I don't know if we can define some integer number or not, but it seems to be very close 1/6 magnetization plateau. Again, here is the 1/3 magnetization plateau is not well defined. Okay, I think it's my take-home message is that this material is the first Kagome antiferromagnet that harbors the 1/9 magnetization plateau. Sure, I last say that this is exactly 1/9 plateau, but it's something very close to 1/9 plateau predicted in the ideal spin-half system. Although we have some band randomness, ground state, eventually we are ended up with an inhomogeneous state, maybe usually the case. If you do some NMR and then you can do ILT analysis, and then I'm quite sure we will ended up with the inhomogeneous magnetic ground state, as usually the case. But for some reason, this is the field-induced 1/9 magnetization plateau seems to be robust. But I don't know, this is the future issue, then lots of people now will have interested in exploring in this uncharted territory. Okay, that's it. Thank you for your attention.
Thank you very much for your very nice talk.
Oh my gosh.
So do we have questions in the audience or online? Okay. Philippe?
Okay, thanks for this talk and an impressive set of data. I was wondering, maybe it escaped to me, but what was the distribution of interactions that you can estimate from your susceptibility? Or it seems that you had some simulations.
Unfortunately, the simulation was done by this Chinese group. If you want, you can read the Liu's PRV paper, appears this year. But to reproduce this kind of some magnetic susceptibility, they actually introduced huge variation of the J1. I don't know, this is physically is adjustable. They introduce even the 70% of the variance of the magnetic exchange randomness. But if you just look at this kind of some angle-wise, Goodenough-Gadanov Anders rule, the angle difference is not that dramatic, 2 or 3 degrees. Although to reproduce this magnetic susceptibility within this minimal model, delta J is quite large. Amount even 70%. I think is other group will also dive into this business, and then we might have a more refined some picture in the near future, hopefully.
Okay, thank you. Because there was a paper by Kawamura and collaborators about generating a quantum disordered state by random exchange interactions. So they were putting a Gaussian, but I think they need much larger delta J than 7%, more like a few 10%.
Sorry, not 7%. It's more 70%, 70. Sorry.
So it would fall right in their scenario. I think they need, in the first step, if I remember correctly, they were needing 40%, and then it was a bit lower. But it could generate this quantum disordered. But it would be nice if from the angles, you could estimate roughly what would be the variation of J. I think it could be feasible. You know, there are series and where J's have been estimated, and one could find out what could be delta J from these simple arguments.
Okay, thanks for your comment.
Has MuSR been done to look at absence of spin glass or something like that?
Actually, we applied the USR beam type in the half a years ago. For some reason, Triumph does not like so much, but they make an amendment, kind of some characterization. And finally, the beam time was approved in Triumph. Then most probably we will, beam time has not been allocated. Then most probably in the December, we will do an experiment. For some reason, our experiment delayed in the 6 months. But anyway, I don't know, this other people also apply the USR beam time in other spot or not. But our group personally, we will do in the December USR experiment.
And what about AC susceptibility at low temperatures?
I'm very sorry. It's our group. Everything is kind of some, or resources limited, and okay, then again we are supposed to go other country for doing experiment, but I don't know other group has been done or not. But this is in the last 6 months, in the several group is working on this compound, but our group will do in the next coming months. But yeah.
Okay, look forward to it. Thank you.
Okay, thank you very much.